I'm here to talk today about ReDoS attacks in Node.js. So we are a bit expanding on the theme presented before by Jamie. I want to convince you that this is a serious problem in Node.js and it needs to be addressed. This is joint work with my supervisor, Michael Pradel from TU Darmstadt. So first, let's see how a ReDoS attack works in practice. In general, you have a benign user that interacts with an application, and it submits such a benign input. And on the server side, the developer usually matches this against a regular expression, either for sanitization or for extracting certain information from the input. And after a constant amount of time, it sends back a response to the user. But in a ReDoS attack, the attacker instead submits a very long payload, or a well-crafted payload that tries to exploit some particularities of the regular expression matching engine. And instead of responding in a constant amount of time, the server now responds in a superlinear amount of time dependent on the input size. And in this way, the attacker can send a lot of requests and introduce a lot of useless computation on the server side. This is a kind of known attack that the community is aware of, but we call it freezing the website or the web server. But our contribution here is to show that this ReDoS attack is common in libraries. We present 25 vulnerabilities previously unknown. We also show that from these library-level vulnerabilities, they expand to websites vulnerabilities, so an attacker can leverage these library-level vulnerabilities. And our methodology enables us to link these two concepts, library vulnerabilities with website vulnerabilities. So now let's understand a bit about the regular expression matching, how does a ReDoS payload is created. For this simple expression over here with two unbounded repetitions of A and then a B, this is a well-known ReDoS vulnerable regular expression. What the engine does is to construct an equivalent state machine with a start state and an accept state, and matching consists of finding a path from start to accept state. For example, if we have an input AB, the engine would find this path over here and conclude that this indeed matches, the input matches the regular expression. If, on the other hand, we have AB, now we have to repeat this transition over here between state 4 and 5 and consume the character A twice. But an alternative solution that an engine may find is to take this transition over here, 8-9, which also consumes A. And this uncertainty basically is what the attacker builds on. And if the attacker now sends this long string of A characters, the regex engine would reach state 10, and without having this benefit of the high-level overview that we have and conclude that there's no B in the input, so give up and say this doesn't match the regular expression, most of the implementation would backtrack and try all the possible paths from the start state to the accept state. So basically going all the way here, repeating, go a lot of times here, then continue between 8 and 9. And this input would take superlinear time to match, dependent on the input size. So in our methodology, we start with npm modules. These are libraries for Node.js, open source libraries. We find module-level vulnerabilities in the first stage. Once we have these vulnerabilities, we install a local version of Node.js and imagine how the developers would use these vulnerable libraries. Once we have these scenarios in which we say how the developer used the vulnerable library, we create an HTTP level payload in which we deliver this payload over HTTP. And in the last stage, we take a set of websites, and by delivering the small and carefully designed payloads, we show that these websites are indeed vulnerable to ReDoS attacks. Of course, the tricky part here is how to perform this third phase on live websites, not on local machine, without harming these websites. In our setup, we use Node.js in single instance for the first two phases for creating the HTTP level payloads. And we look at popular NPM modules and popular websites on Alexa Top 1 Million. We look at 2,000 websites, 2,800, that set a particular header, which is a signature of the Express framework, the most famous framework on Node.js and the 5th most dependent NPM module. So if you missed the talk before by Jamie, you may ask yourself, why Node.js? So why would you care? So one important issue here is that Node.js is single-threaded. So since it builds on the JavaScript engines, the event loop architecture basically says that all the JavaScript code would run in a single thread. This includes the regular expression matching. So if we can build a payload, a regular expression payload, this would block not only the current thread that serves the current client, but rather the whole instance of Node.js. Moreover, the third-party libraries that are so common in Node.js are also a problem, because even though these libraries are in general available to be analyzed, it's not clear whether, if researchers find a vulnerability here in one module, whether this vulnerability would affect the website that uses this module. Maybe the website sanitizes and makes sure that the module is used in a secure way. So I think our methodology basically tries to bridge this gap between a vulnerable module and a vulnerable Node.js application. So a bit about the ethics of analyzing live websites. So in our experiments, we use very few payloads. We only have 80 requests in total. We send them sequentially in what we call iterative probing. So we start with the smaller payloads, and we increase the size, paying attention at both how long these requests take and whether the web server replies with an error. If that's the case, we immediately stop our analysis. And lastly, we report all our vulnerabilities to the library creators, and the majority of them have currently been fixed. So an attacker cannot use the payloads we described. So now I'll go step by step through the methodology. First, in the Npm analysis phase, we look at open source code, and we consider a module to be vulnerable if we can create a payload that is 80,000 characters long, and it takes more than 5 seconds to match. Why these values? The 80,000 characters is the header size in Node.js. And since we want to look at scale at web applications, we took this limit into account in this first phase. But of course, if an attacker decides to send these payloads through, let's say, post requests, then you can relax this value here. And the 5 seconds is an overestimate of what currently the community considers a vulnerability, a ReDoS vulnerability. We manually looked for these regular expression patterns that are known to be vulnerable to ReDoS, and for the information flow that confirms that there is a path from the API of the module to the sink, to the ReDoS sink. And we manually crafted exploits and measured the execution time, so the matching of the regular expression. In total, we have 25 vulnerabilities, as I said in the introduction, which resulted in 13 advisories. These are basically public statements by the community that says this specific version of a module is vulnerable. And unexpectedly, we also got a bug bounty in the process. One of the company decided to reward us for the effort. I'll show you a couple of examples. So here is one of the vulnerabilities we found. And of course, maybe it's hard to see at first sight if you never saw this problem before, but the trick is the vulnerability is here, these two unbounded repetition next to each other. So basically here we repeat the space characters, and here the not equal character. And this gets confusing for the regex engine, which would try to match a space in different ways. And a more serious vulnerability we identified was in the UA parser JS package. This is a package for parsing user agents. And this is an exponential vulnerability because we have two nested repetitions here. an alphanumeric nested, and then again nested. And this would allow an attacker to deploy a really serious payload. Once we identify these 25 vulnerabilities, we proceed to phase 2. In phase 2, we look at local Node.js installations and create the usage scenario for each vulnerability. And I'll show you now how a usage scenario looks like. So for this package over here, mobile detect, we basically hypothesize that on the server side, the developer just takes the user agent, passes it to the constructor, and then calls this method phone here. If the method is not called, then basically our payload is not delivered. And our HTTP levels that we produce are for this particular scenario. And we were able to create 8 payloads. And this difference, this mismatch between the 8 payloads at HTTP level and the 25 at module level comes from basically our target to study websites at scale, and from the fact that we basically restricted ourselves to HTTP headers payloads. And now that we have these 8 payloads, I want to show you how the input dependency looks like. So the relation between the input size here, the number of characters of the payload, and the matching time. So for example, the vulnerability we discussed earlier, the UA parser.js, you see it's basically exponential. So we need 40 characters to trigger a 2 seconds payload, 2 seconds matching time, sorry. And the less serious one, user agent, still requires less than 1,000 characters to deploy a 1 second delay. But most of the vulnerabilities we identified were super linear. So this basically means that you need more than 20, 30,000 characters to introduce a 1 or 2 seconds delay in the application, in the server side. So once we have this relation between the input size and the matching time, what we did was to dimension the payloads, starting at 100 millisecond target. And here we basically measured on our local machine how many characters we should send for a 100 milliseconds matching time. And we sent 3 requests for warm-up and 5 for measuring. We also sent 5 random characters of the same size. So basically, we can compare the response to our crafted input and to the random input. We have then a payload at 200 milliseconds level, 500, 1 second, and 2 seconds. So these are the 5 matching times we consider. And we consider a website to be vulnerable if by sending these payloads here in increasing order, we observe a statistically significant difference between the crafted and the random input. And this difference increases over time, over the payload size, sorry. So as we increase the payload size, the difference should increase. So now I'll show you how a non-vulnerable website responds to our request. So here we have the payloads, the 5 payloads I described earlier, and the response time. With black, we have the random inputs with the confidence intervals, and with the red, we depicted the crafted inputs. As you see, there's a lot of overlap, so we cannot really conclude anything about the website, whether it's vulnerable or not. We can conclude that it's not, actually, because since it's not easy to discriminate between the 2 of them, here, for example, at payload number 5, the random one is even slower than the crafted one. But a vulnerable website, on the other hand, replies like this in our experiment. So basically, the 5 payloads, the random characters payloads, with black here, they are all served in less than 500 milliseconds. But the crafted ones, they take super linear time to respond. So basically, for payload number 4, we get more than 1 second response time. So I hope I convinced you that this is a good way to show that a specific website is vulnerable. And an interesting side effect of our methodology is that we can basically say for each payload how many websites are vulnerable to that payload. So for example, for the vulnerability I showed during the talk, the UA parser.js, the very serious exponential ReDoS vulnerability, we can say that 41 websites are vulnerable to that payload, to that vulnerability. And you can do also the other way around and say that specific website is vulnerable to these two payloads and thus uses those two packages on the server side. And this is an effective way to fingerprint web servers. In total, we found that 339 websites, 11% of the ones we consider, are vulnerable to a ReDoS attack. But of course, some of them deploy some kind of control, some defense against such attacks. And the ReDoS attack is not just the packages we send here. An attacker would need to send tens or hundreds, maybe tens of thousands of such requests to deploy a ReDoS attack. And what we saw deployed in the wild was basically some kind of limit on the header size. Here we have the accepted header size and a number of websites. So if we send, for the first payload for this char set vulnerability, the first payload we send is around 9,000 characters. And most of the websites accept this payload, the 9,000 characters payload. But as we increase this and we cross the 10,000 characters input size, header size, they stop responding. So in the end, for the fifth payload, we got only 400 websites or something like that responding. And if we look across all the vulnerabilities we identified and across all the payloads, we see this descending trend that basically, as we send more payloads, the websites stop responding. And this is even for the small ones that have less than 100 characters. Basically, even here, the website stops responding. And we believe that there's some kind of check on the number of requests a website gets from the same IP address. And this is a great first-level protection. But of course, a website should consider more principled way of tackling this problem. For example, having better implementation for regular expression matching instead of the backtracking solution I presented here. There are several other ways to match regular expression more efficient, especially when certain constructions, certain syntax is not used, such as back reference or forward reference. And this is successfully deployed in Rust, but of course, this is very expensive to implement and deploy. Another solution was presented earlier in this session by Jamie, but of course, as he described also, there's a sweet spot there how to choose the correct timeout value, and it probably is application dependent. But we believe this is a great solution. And finally, better tools for identifying these vulnerabilities and creating exploits are needed in the community needs them because there are a lot of vulnerabilities out there. So to conclude, today I showed you that ReDoS vulnerabilities are widespread in Node.js, in particular in Npm modules, which are the third-party libraries of Node.js, that these vulnerabilities can be exploited in live websites, that 11% of the websites are vulnerable to one of the attack vectors we constructed, and that ReDoS vulnerabilities can be used to fingerprint web servers. Finally, we discussed a set of mitigations and pluses and minuses for each of them. Thank you very much, and I'd be happy to take any questions.
Got some time for some questions.
So I'm still a little curious about the ethics of sending malicious payloads to websites that might make them time out.
Yeah, I think that's a great question. So I hoped I tackled that problem in the slide. Basically, we started with 100 milliseconds, which is, I have a list here, is 30 characters or 500 characters, and we increased this size sequentially. We always interacted only with one instance of Node.js at a time, right?
Were those measurements taken on like the most pathetic virtual machine you could find so that you were very confident that they wouldn't be an underestimate of the impact on the server?
Sorry, can you repeat?
So were you measuring this on a server class machine or a desktop class machine or a AWS micro instance?
From the client perspective, you mean?
Yeah, you're measuring, you're crafting a payload that'll cause a certain timeout.
Yeah, I see. No, we measure this on this laptop actually. Yeah, so on a production laptop.
Okay. Do you know how it compares on a micro instance or similar?
No, honestly, no.
Okay, thanks.
Thank you.
Hi. One thing I didn't quite catch was how did you identify the ReDoS vulnerabilities in the first place? Was that manual or were you using any tools?
Yeah, so that was mostly manual. We extracted a lot of regular expressions in a database, and we manually searched for known patterns, and with lots of trial and error, we wrote these exploits.
Thanks.
Thank you.
Any more questions? If not, let's thank the speaker. Thanks very much.